All right, physics teachers are awesome, number 90. Looks like today is, there we go, pressure in fluids. So that sounds exciting. So AP Physics 2, oh, that's pretty exciting. So this is a school that has maybe 2 whole years worth of AP Physics, which is not standard. Sorry, just get my camera aligned. So let's get going.
Hey guys, Ms. Peterson here, and this is AP Physics 2, Lecture 1-1, all about pressure in fluids. We're going to be talking about density, absolute versus gauge pressure, and how those play out in static fluids. This corresponds to AP Chemistry topics 1.1, 1.2, and 1.3, and the textbook sections are there for you. So let's go ahead and start with density. Density is probably...
So she said it corresponds to some chemistry sections too. I'm not sure if she's teaching both classes or if really the material is in both curricula, but certainly, you know, this is the sort of crossover between physics and chemistry when it gets to these sorts of things.
A familiar concept to you. It is a measure of how much stuff is in a space, okay? Or you could think of it as
cool.
The mass per volume. And that's basically what the equation is. In physics, we use the Greek letter rho for density, and it's equal to mass over capital V for volume. The primary units that we're going to be using are kilograms per cubic meter. Okay.
You know what's interesting about the metric system is a lot of the base units are you know, things that we're sort of used to, but I've actually been doing some silly calculations involving this and realizing that a cubic meter is not really a realistic thing in your normal life. Cubic meter is actually this gigantic thing, right? And so, for example, yeah, exactly this example she has here, you know, 1,000 kilograms, that's a ton, right, per cubic meter. And that's why, you know, often in the metric system, people shift over to liters, but in physics, we're just stubborn. We're always going to do meters cubed, even though liters are much more sort of things that would fit in my camera shot right here.
So, density of water, 1,000 kilograms per cubic meter. That number is going to come up a lot. So just go ahead and memorize it. Now, often we're going to be talking about fluids and forces on them.
You know, I was just thinking about that memorization. That is something that I use all the time. We know that water and the metric system is intimately connected, so we would expect a nice, beautiful round number when you're using a metric mass divided by a metric volume. And so I wonder how well students are able to sort of internalize that sort of thing. Like, I know it's got to be 10 or 100 or 1,000 or 10,000. It's got to be a nice round number. If we asked somebody, you know, how much a cubic meter of a living thing would be, because living things are often made of mostly water, would we expect them to land at 1,000? Is it unexpected for them to say, oh, well, that's only 100 kilograms? You know, that's interesting to me because I weigh over 100 kilograms these days, and I could imagine mistakenly thinking that my body is a cubic meter, but, you know, I'm tall, but I'm not, I'm not that big in the other directions. So it is interesting to wonder whether this is a straight memorization or if this is sort of tying to ideas that we already have.
So let's think about the force of gravity, aka the weight of an object, in terms of its density. So, review. Force of gravity is equal to an object's mass in kilograms times the acceleration due to gravity, g. So, if we want to express that in terms of density, we're going to have...
Ooh, one note.
Well,
Love
here
one note.
we have mass. So that mass is going to be density times volume times g. Okay, so rho.
Just a little bone of contention I have with one note. It's great for this annotation stuff. You can even see that it's got line thickness stuff going on, right? This part of the line here is thinner than this part, so it looks really nice and natural. But it doesn't. When you're using a stylus, like she obviously is, it doesn't act also as a pointer, and so you can notice that her letters just kind of show up. and it's hard to know exactly what she's pointing at. Now, I said in another video how when I'm using this, I will constantly make little dots just to catch my students' attention. I wish that there was and maybe you guys know of one, I wish there was a OneNote sort of setting or something so that if I'm not actually writing, but it can detect my pen, that it would show where it is. I actually think there's a tiny little dot when I do that, but it's so hard to see, and it'd be great to turn that into a pointer.
OVG. That is going to come up as well. So
quite a symmetric equation there.
We're going to be talking about pressure. As a reminder, pressure equals force over area, normally in units of Pascal or a Newton meter squared. But what actually causes pressure on like a molecular level? Two things. First one is we got pressure due to the thermal motion of molecules. You might remember from elementary school, in a solid, we have molecules vibrating in place. In a liquid, we have molecules rolling around each other. And in a gas, we have molecules flowing all over the place. Well, these molecules are going to collide with the walls of their container.
Love it.
That's going to happen. And that is what we call pressure. Okay? Pressure is the force due to the collisions of those millions and millions and millions and millions of air molecules with your body. Okay? Now,
I was just thinking of a subtlety here. So this is a fantastic way to describe the pressure. I love the cartoon that she's drawing, and I think that it really explains the force on these sidewalls. And yet, it seems that when we describe pressure, we're actually talking about a measure of just like all of the gas, not just at the edges of the gas. And so if you were to stick your hand in there, you'd feel that. And so, I mean, there's no question that if you had some other thing in here, this idea of molecules bouncing off would still work. But what's fascinating is your hand is not this beautiful flat thing, right? And so being able to calculate these gorgeous bounces are going to be much harder to do. So I'm sitting here thinking, if we talk about pressure as a definition of bouncing off nice flat walls, does it immediately lead students to understand that that's what you would feel with your non-flat shaped hand or head or body in here? So that's really, really interesting. But I love how she's doing such a great job of explaining how the just the natural motion of gas molecules causes sort of this force. Love it.
That's not the only cause of pressure. Okay, when you swim to the bottom of the pool, you know that that's at a higher pressure, and that is also due to gravity. Okay, the pressure at the bottom of something is going to be greater due to the weight of the fluid above it. Right now, you have an entire atmosphere of pressure pushing down on your body.
Love it.
We call that one atmosphere of pressure. It's about 101 kilopascals. But that's just what we're used to, okay? It's a lot of pressure, but it's also exerted on the inside of our bodies, on the walls around us, on the outside of the walls around us, everywhere. So we don't really feel it. Now, there are two ways that we measure pressure. Absolute pressure means the pressure of zero is defined as a vacuum. Okay, so anytime we're doing pressure calculations in like space or where we have a vacuum or we have a controlled pressure system, we can talk about the absolute pressure. Your bicycle pump, on the other hand, okay, it does the gauge pressure, aka the difference in pressure between the inside and the outside of.
So when I first learned this, I missed it somehow. I don't know, maybe I was out that day or something. I really thought the bike pump measured absolute pressure, and I was just so confused. I was constantly confused in this. I was doing homework problems, and it was just bothering me. And in fact, I remember even into graduate school, when we were doing some low pressure stuff, I was just so confused all the time. And so somehow this idea of gauge pressure was just not part of my education. And so I really love how hard she's hitting this. And absolutely the bike pump is my most common experience. Just had 2 flat tires last week, thanks a lot. On the same day, thanks a lot. And I think that the way she's talking about this is great. And of course, almost every homework problem in physics is going to need this one. Well, that's not true, Kind of depends, I guess, on the question being asked. But so often, in the ideal gas law, all of those things, when you have putting a pressure in, you need absolute pressure. And yet, the most common gauges you can buy present gauge pressure. And so I just think that I love how she's hammering this.
The tire, okay? That difference in pressure is the gauge pressure. And you can think of absolute pressure, okay, as like the pressure of the atmosphere plus the gauge pressure. Standard pressure, P naught, we use a lot.
All right, just going to stop there. Notice we're at about the 10-minute mark here. Just some really, really great things in here. I love, first of all, her setup. I didn't comment on that very much. Love the camera. She's super clear, and love how she clearly has a couple of different screens. Oh, no, she's sharing her screen. I see. And writing right on there, which is wonderful. You heard me complaining a little bit about OneNote, but I think that what she's doing has really, really done a good job to help students. I presume this is some kind of handout or something that they can also follow along with, but I also presume, since most people are, that she has an in-person class. And this is kind of work to help them set up for, the work that they're going to do in class or lab or something like that. Loved the cartoons. She was really, just very, very, let me just go back here to point out when she drew this one here. Let's watch this again. Just watch how fast she does this and how immediately you can tell that she's talking about, in this case, water, right?
To the bottom of the pool, you know that that's at a higher pressure. And that is also due to gravity.
Talking.
Okay? The pressure at the bottom
Look at that.
of something is going
Look at that. Let's pause and say how awesome that is, right? She was talking while doing it, and I would say that everyone understands this is something at the bottom of the pool. She just said bottom of the pool. She did the little wavy line to indicate water. And I think that we don't comment enough about this with teachers, right? Helping them understand and helping them develop this really, really amazing skill that if you were to ask students to do this, they would draw this differently. Some would try to do the pool in 3D. Some would just have this be an absolute straight line, and then they'd be wondering what's going on. And I just wanted to praise her for that. So that's super cool. All right, everybody. Well, I hope you have a great day. And remember, physics teachers are awesome.